Hi guys, welcome to Make or Repair. Today I've got this little lamp to have a look at. So I think, to be honest, it's just the on-off switch just here, which is a little bit dodgy. It seems to, I'm pretty sure that's the on-off switch. I don't really know anything about this lamp. It's a camping lamp. It's got a compass in the top which is not pointing in the right direction, and it doesn't point in the right direction if I take it outside, by the way, so yeah. But anyway, this needs repairing. It's battery powered. I know nothing about its circuitry really, but we'll have a little look, see what's what. Looking at this should probably be like a brightness control as well as a switch. You know, maybe just some physical problem. Maybe there's some other problem with this. I don't know. We'll just take it apart, see what's what. Let's say it's big. What are these, Ds? Are they something like that? Yeah, D-type batteries. Let's just have a quick look at the voltage on those. I won't bother putting a load on it for the minute, just want to take a quick view. So I'm reading that 1.57 volts, so they're probably, I mean, you know, they're probably all right in order to get started with the lamp. Let's have a look inside here. So I can see there's two screws in the bottom, so I'm just going to take them out. And then I hope the whole of the inside will just slide out if I'm very, very lucky. Straight into the plastic, no problem there really, though. These are very, very cheap devices. Oh, well, there we go. Whoops. And a small piece of plastic is kind of thrown across the room. Well, this would appear to be the, not just a switch. Appears to be a combination of a switch and a pot, as far as I can see. That wire is not connected to anything, but I could have well taken that out as I pulled it apart, I suppose. There's a very small screw here that's loose. Pretty sure that works. Appears to be permanently on at the moment, but the wire's broken anyway. So we just come from positive tab on here. I think that's positive. The negative tab on here, which is red. Yeah, that's really. Goes into here, into the switch mechanism, out of the switch mechanism, into the centre of the pot, out of the centre of the pot, and up to the LED. And the white, I imagine, is supposed to go directly to the LED. I might just replace that piece of wire. It doesn't need to be thin and fiddly like that. So I just need to take this centre section out now, because I'm still going to get nowhere unless I can kind of gain access to the set of LEDs, because I need to reconnect this wire. So I'm kind of assuming that small screw is supposed to attach a piece of plastic onto the top of this, so the screw will go in. So I think I can get the knob off. It actually has a plastic kind of like circlip around it to hold it in place. So there we go. So this is the knob that operates this thing, and of course it's miles too big. Now if I look in the end of this, let me zoom in on there, you can kind of see that there's like a little bit of a flat just there, and also on the opposite side. So clearly there should be a piece of plastic that will screw onto this and make that work. Alright, so I think this has definitely had a good thump somehow. Let's see if now we can manage to get access to the LEDs. That's not ideal. So what's happening there is that's unscrewing from the wrong end. Oh. To hide the screw. Right, okay. So now we can get at it. Okay. So now I should, hopefully, I can find my pliers. Okay. How much access does that give me? Okay, let's pop it off there. And see if we can understand what they've done with these light strips. Cool. So fairly simple, red that side, white that side. So each 4 is to the 1, 2, 3, 4, 5, 6 LEDs on each. All connected in parallel. So negative, positive as far as I can see. So okay, I'll just put some new wire on that, I think then. Seem to have a bit of yellow and a bit of white, so that'll do. Not really that interested in their colour coding. So let's just make sure before going much further that actually I can power them. And how much current they draw and all that sort of stuff. LED there is very faint, but it is on. That's pulling 0.2 amps in total. Great, and we'll just give a quick tidy up of this junction here because it's very messy looking. And I mean they've literally soldered this directly on the back of one of the LEDs. They haven't made any facility. To actually do a proper solder joint at all, let me just tin this. Tin it, trim it. So those people wondering why I'm sticking a bit of blue tack on there is because I actually like to apply the solder and the soldering iron simultaneously to the junction, if I can. I also like not to burn my finger if I can. So okay, so that's that done. Now, I think there's room here now to just tie those two together. And that's just going to give it a tiny bit more, just an incy bit more resilience. Because any pull will be on both of them simultaneously, not just on one of them. So I think that'll be alright. Right, let's start putting it back together again then. Okay, so I'm just editing this video and I figure it might be a good idea to put in an explanation about why, although this dimmer circuit in this lamp is very simplistic, and you might think it's okay, in actual fact it's not really the cleverest. So, other than the brightness of the lamps, there's one thing that we really need from a battery-powered lamp, and that is we want the batteries to last quite a long time. Now, one way we could do that with this lamp is actually to put a switch, because there are 3 panels, and almost certainly 1 or 2 of them are not going to be pointing in a very useful direction. So if we could switch them off, that would instantly improve our battery retention just by having a little switch in there. So if you've got one of these, your batteries run out a bit fast, then think about fitting a switch. Why not? You might think as well that turning down the brightness would be a good thing. It will help the battery last longer, and it will, but as we'll see, it's going to reduce the efficiency. So we want the batteries to last as long as possible. Now, these lamps only cost £6 or £7 each. The batteries cost nearly as much probably. Let's take a look at this circuit then. What we want to happen is these 18 LEDs just here, we want as much of the power that the battery is delivering to get to those LEDs so it can be given out as light. Now, I don't actually know what type of LED they've got fitted. I have simulated this using a top LED 3.6 volt 100 milliamp LED. Now we've got a 4.5 volts of battery, that's 3 1.5 volt cells in series, and In truth, they're going to start life closer to 5 volts for the 3 of them, because, so here we go, they start life out at about 1.6 volts according to the Duracell datasheet, and then they drop very, very rapidly right through 1.5 volts and down into the 1.4, 1.3 volt region. So in my simulation, I've done 2 things. First of all, I've simulated the internal resistance of the battery, because there is an internal resistance, which they say is 125 milliohms or thereabouts. So I've given it 375 milliohms because there are 3 of them in series. So that some of our power is going to be lost in that internal resistance within the batteries. There's absolutely nothing we can do about that. Then we've got this resistor one just here and a slider next to it. Now this is so that in the simulation I can change its value just like you would do on the actual device itself. So I've got it set at 0 at the moment. That's probably not realistic. Let's change it to 125 milliohms. And that's because the power goes into the switch, out of the switch, into the middle of the pot, and then out of one end of the pot. So I'm working on the basis that you can't quite get to 0 ohms. You're always going to be just a little bit more because you're using just the end of the track of the. So I've got a 4.5 volt battery. It's internal resistance on the left hand side here. And I've got my pot basically turned to as bright as possible. And then I've got my LEDs. So on the left hand side here on these graphs there are various values, but I'm probably only going to use this one. So this green line that we can see here is the total power of everything in the circuit. So we can see that it comes to 8.968 watts. So let's look at the first resistor. So in the middle of this sort of pop-up box we can see a few values. So last values is the bit that we want to read. And it says I equals 1.993. So that's the amount of current that's coming out of this battery. So nearly 2 amps of current. If I go to the data sheet, have a quick look at that. So this blue line on this, well, purplish line on the graph is 1.5 amps. So we are considerably to the left. So that's my kind of 2 amp approximation. So yeah, that's pretty poor. That means the battery's only going to last like 2.5 hours. So 8 point something watts, 2 amps, thereabouts, and this resistor, the internal resistance of the battery, is dissipating 1.489. So out of the original 8.968, 1.489 of it is lost just as heat from the battery. If we then move across to the pot, we're losing another, even though this is almost off, 496.3. So that means over here we've only got, out of that original power budget, these in total are dissipating 6.983 watts. So if I divide that 6.8, I get an efficiency of 77.9%. Okay, so full brightness, new batteries, 77.9% efficiency. Well, that's cool. Okay, so let's wear the batteries down a bit, because if we look at this data sheet again, we can see how fast these batteries are going to be coming down. So let's set them to sort of each battery to sort of 1.25 volts thereabouts. Okay, 3.6. Now, it's not a coincidence that 3.6 is the forward voltage of these LEDs. I've chosen that kind of on purpose because it's kind of roundabout where we're going to get the best efficiency out of this. But anyway, let's have a little look what's going on. So over here on the left hand side on the graph, we can see we're using 2.467. Internal battery dissipation is 178 milliwatts, and in our pot we're losing 59.4 milliwatts. So I'm just going to call that 0.059. That means we've got 2.23 watts arriving at the LEDs, and that is 90%. Let's put it back to 4.5 volts again, and this time what we'll do is we'll turn the brightness down using the pot. So I'm going to set this to 2 ohms, I think, something in that region. Okay, 2.1, that'll do. 2.125, that'll do. So let's have a look. What have we got going through the LEDs? So we've only got 28.8 milliamps going through there. Now if I bring this all the way down, we've got 137 milliamps. Now that's more than the LEDs are rated for. But in truth, that's drawing so much power that the battery will run down really, really fast, and the LEDs probably won't suffer. Although we do note that one of the LEDs has actually failed on the board itself, so maybe the heat is too much. These are pretty small LEDs. I kind of fear they're not really 100 milliamp LEDs that they've fitted, but I don't know for certain at all, because there's no part number on them, they're just an LED. Anyway, up to 2 ohms or thereabouts. Oh, there we go, 2 exactly. So 2 ohms, 30 milliamps. So this is now getting quite dim. You would be far better actually switching out one of these banks of LEDs for your dimming method than doing this. Let's look why. So 4.5 volts. How much are we losing in this first internal resistance? Oh, sorry, let me go across here. How many watts? 2.4. So pretty much the same as with the exhausted battery, really. 2.442. Let's have a look at this resistor here. So this resistor is dissipating 110 milliwatts. And let's have a look at this resistor here. So this is the pot, and it is dissipating 588.3 milliwatts, so nearly 0.6 watts. So they've probably got a half watt pot in there, I would suspect, or hope. Might not be anything like that, of course. So in total, 1.744 watts, is being used by the LEDs. So if I do that, 1.744 divided by 2.442, that is only 71%. Pushing on for a third of the power is just being lost in our controls instead of. So given the price of batteries, that isn't kind of really what you want. So in terms of manufacturing, this of course is really, really cheap. In terms of running, it's a bit pricey, in fact, because you're always going to be in that 70 to 80% region. And of course, one thing that's going to be happening is you put these batteries in, it's going to be nice and bright, and within half an hour it's actually starting to get quite a lot dimmer. Or you might put the batteries in, it's quite bright, you turn it down to try and make the batteries last a bit longer, and in doing so you actually reduce the efficiency of your batteries anyway. So not ideal. So how could we do better than that? What I've got here is a switching type brightness control rather than a variable resistance control. So what happens here is we have a signal that comes in. I'm going to make it a bit more symmetrical just for a minute, like this. And it's switching on and off. So it's going through high voltage, low voltage, high voltage, low voltage, alternatively, and generally at quite a high frequency, let's say 100 kilohertz or something like that. It's going to the base of this transistor, and this transistor is alternatively saturating and allowing basically all the current through from the positive up here, just there, that's the positive, and it's flowing through here, charging up this capacitor a bit, and also the LED is using the power as well. So if I lengthen the period for which it's turned on and have a very short period when it's turned off, then essentially this is just like closing. If I make it constantly on, then it's just like closing the switch. If I make it nearly almost all the time on, then it's very bright. And as I make it have a shorter on period and a longer off period, then actually the LED starts to dim. So you can see really it's flickering extremely fast, faster than we can recognize as human beings, and yeah, and that gives us the impression that it's dimmer. But if we use an appropriately sized capacitor in here, then we can actually smooth out that flickering as well to stop any stroboscopic effects that we might have. Now in truth, what you would normally do then is you would have a current sense on this transistor as well, feeding into the base of this transistor, so that although you've asked for a certain amount of brightness, if this LED starts drawing too much current, then this transistor base will be pulled down towards ground. It will turn off the transistor and stop the LED getting too much current and burning out. So that sounds like quite a lot of circuitry. We need a multivibrator over here to make this signal. It's got a variable duty cycle, so different on-off periods. What else has it got to have? We've got another transistor that's going to pull this transistor down to ground. We need this transistor. There's quite a lot of circuitry involved in here, so that's going to be expensive, right? Well, no, because you can buy all of that circuitry in a ready-made IC. So if you're buying in the thousands, you're probably talking a few cents, let's say $1, 80 pence in the UK, something in that region. Because we don't need a lot of switching power with this one. You could even make this out of a couple of operational amplifiers and a couple of discrete MOSFETs, something like that, or a couple of discrete bipolar transistors. What about efficiency on this? The multivibrator circuit and comparator circuits and things like that, they have a quiescent current requirement, but we're talking a couple of milliamps, and therefore a couple of milliwatts as well. Virtually nothing, almost negligible amount. This transistor though, how much does that use? Well, again, almost nothing, because it's either turned fully on and just conducting, or it's turned fully off. So there's virtually no power dissipation in that transistor at all. And that's a bonus, because of course that means we can use a relatively small transistor there, because it's not going to get hot. And and the capacitor, as I say, is kind of optional, but we're talking pennies of capacitor here. We're not talking a big electrolytic capacitor at all. So so for about $1 we could replace, or an additional $1, we could have a variable brightness but roughly 98% efficiency LED controller. So far better than we were achieving with this. So switch mode dimmers can, first of all, limit the current to the LEDs so they don't burn out, and secondly, they can give us really high efficiency. A pot cannot. Anyway, let's get back to the video. That, very surprisingly, is not just a straight piece of plastic tubing. It is actually wider at this end than that end. Alright, let's try and reassemble this. I don't like the fact that some of the LEDs are a bit faint, but it's truth. Try and feed the wires through. I'm sure in the factory in China where these are manufactured, they can assemble these in 2 seconds flat. But so I've just got to assemble this into the corresponding slot in the bottom. Oh, got it. All of a sudden it just drops in. I've got my 2 wires coming out, so that's all right. This is latched in the right direction. Okay, and now this top section, they've obviously drilled some, are they drilled or are they just really badly moulded? Some ventilation slots in that. These are actually made out of plastic. This is great. So just feed that up there and try and get it through the hole. Just going to put that on loosely for a second while I get the other one in. It's interesting because the wire of this is a similar, this is a wire sort of hanger, and the wire on that is of a similar gauge. So they could have, I would have thought, it wouldn't have really been a lot different to put a chrome wire thing through there, but every penny counts, it would seem. Every penny counts. I don't want to tighten that up too tight with it only being plastic, of course. Yeah, I can feel the whole thing flexing as I tighten it. Okay, so I've successfully tinned that. So let's just wrap strip a fairly long length off the end of this, I think, and just wrap it round fairly tight, and then we'll solder that, and hopefully with a long connection like that we can achieve something fairly stable. I'm just heating the whole joint till it all melts, and I'm just feeding in loads of solder, flooding the end of the wire with it and also the junction. So yeah, that's not going anywhere now. Good. Okay, so I have made a little plastic piece to go on the end of the pot and shaped it so that it will fit tightly into the actual knob, and I've drilled it out with two holes, one just wide enough to take the head of the screw and the other one just wide enough to let the bottom of the screw through. So fingers crossed this will now assemble, and I should be able to then put the whole thing together. We'll see. So that seems to work well enough, but I will have to take it off again in order to actually mount it in the case. Okay, so the pot slides into the two slots, and then we're just going to have to solder up the wires. Okay, what I managed to miss on the video here is I'm just attaching that little yellow shaft onto the pot that I pushed in, I screw it in place, and then I just push the cap onto the end of that firmly. And it's held in place using this little plastic circlip, so I'm just using some tweezers to position it and then just push it on with a screwdriver. Okay then, so before I put the batteries in and actually finish it up, let's just power it up from a power supply, and there we go, we've got some lights. Now the power supply is actually current limited. I think I've current limited at 500 milliamps, and from the simulation earlier we saw that it actually does draw an awful lot more than that if it needs to. But there we go, working nicely. This pot, to be honest, you know, only the last 10% of it does anything useful. Okay, so last up really is just to finally reassemble the battery compartment into the body, put the batteries in, and let's give it a test, I suppose. So batteries are in, and let's just get this slightly awkward bottom put on and give it a test. Here we go. And there we have it. Yeah, as expected really. So that seems to be working okay. I'm still not convinced that it's a particularly good product, but it is what it is. It's very cheap, and yeah, in an emergency it'll give us a little bit of light as needed. This was a very simplistic repair, not up to the usual sort of complexity, but I think it's still worth doing and worth showing, because, you know, I want to encourage people to fix things rather than keep throwing them in the landfill. And certainly this is an example of, yeah, there wasn't anything, I mean, there was a loose wire, but other than that there wasn't anything electrically wrong with this, but there was certainly a physical damage to the knob. It had clearly been knocked, and it's made of brittle plastic. It had broken off, and the new little thing is just made of a scrap of nylon really that I put in my drill bit and just ran against a piece of sandpaper to get it to size. So nothing complicated there at all, but it did the job. We've got a thing that's working. So anyway, hopefully you enjoyed that. Hopefully you can understand why this isn't a good design and why a slightly more expensive one with pulse width modulation control would be a better option in terms of running costs. Anyway, hope you enjoyed that. If you did, don't forget to click the like button, and of course subscribe if you haven't already done so. In the meantime, take care, and I'll see you next time. Bye for now.